Hi there, this is Nina LeBrun. I'm giving my con-style video for resting membrane potentials for neurobiology with Dr. Cordes. I'm going to start out by just drawing a cell membrane for my neuron. This is selectively permeable, just like any other cell membrane. It's got all kinds of channels and pumps and things that are deciding what go in and what go out and why. But you can think of the space in the middle as the intracellular space, and then this space out here as kind of the extracellular space. And what I'm going to start by doing is drawing some of the ions that we talk about most with resting membrane potential. So first I'm going to draw chloride, and then I'm going to draw a little bit of potassium, some sodium, and some calcium, and then also just some kind of miscellaneous organic anions, which also sit in the middle here. The reason I've drawn some of these on the outside in that extracellular space and some on the inside is not because they only exist on the inside or the outside, but simply because the things like potassium and those organic anions are a lot more concentrated on the inside of the cell at resting membrane potential, and then these ones are a lot more concentrated on the outside of the neuron during resting membrane potential. So again, like potassium exists on both sides, just a lot more of it on the inside. Same with sodium. There's sodium on both sides, but a lot more of it is going to be on the outside. So because of things like that, that create a gradient, those different chemical concentrations, things naturally want to move from an area of high concentration to an area of low concentration, and that's going to be one of the things that's controlling where ions are flowing. The other thing that we're going to look at is an electrical gradient, which is actually caused by these charges, these negative and positive charges. Ions exist like this in the body because our bodies are mostly water, and things like NaCl ionize when they get into water, and so our body is full of all these little like free ions floating by themselves. They in the end make our body neutral overall, but they do like have charges which influence which way they want to go across the membrane. So for example, with chloride, its chemical gradient, because it's more concentrated out here, it's going to want to move in, but then its electrical gradient, because this intracellular space is more negative on the inside, then this electrical gradient is going to want to make this flow out. Potassium, because it's already concentrated on the inside, it's going to want to flow out chemically, but it's going to want to stay in electrically because positives and negatives attract. Sodium wants to go in both chemically and electrically. Again, that positive charge is pulling it into this negative area, and because it's more concentrated out here, it wants to flow into the area of low concentration. And then our calcium also is going to be one that wants to flow in both chemically and electrically. Those organic ions we're not going to talk about a lot, but in the end, they would end up wanting to flow outwards, both because of their concentration gradient and because of the fact that it's negative in here, and so that negative's going to want to push away. But you'll see that things like sodium and calcium are not very conflicted. They really want to go inside, especially sodium wants so badly to flow inside if it could. But because of this membrane holding it back, it can't when it's sitting at resting membrane potential. It can't just rush in. Things like chloride are kind of conflicted, as you see. It wants to go in chemically and out electrically, and potassium is the opposite. It wants to go in electrically and out chemically, so that makes them kind of conflicted, but in the end, the thing that overrides the other is this chemical gradient is a little bit stronger than the electrical one that's pulling on it. So at your resting membrane potential like this, you're at negative 70 millivolts approximately. It kind of depends neuron to neuron, but that is relative. That means that this intracellular space is negative 70 millivolts relative to the outside. Our bodies are not like overall negative or overall positive. They're really neutral in the end, but if you were to stick a probe in this part and this part, this one would come up as negative 70 and this one would come up as technically 0 millivolts. So again, both of these gradients are telling the ions which way they want to go, and we have this whole action potential that happens that I think will be in a different video, but basically it kind of screws with all the gradients, and then after the action potential is over, there's going to be these sodium-potassium pumps which are trying really hard to push out 3 sodium for every 2 potassium that it brings in. And after the whole action potential goes, it hyperpolarizes. The pumps, as well as some of these just like leaky ion channels, are going to restore this negative 70 millivolts that the cell just really wants to be at. The ions are just most comfortable being in a gradient like the resting membrane potential creates. So again, there's a lot of stuff that happens during the action potential, but if you're just talking about resting membrane potential, that's what you need to know, is that you're going to have chloride, sodium, and calcium more concentrated on the inside, and then potassium and these organic anions on the inside that are creating this negative 70 millivolts difference between the intracellular and the extracellular space.